So let's take a look at this example. So remember from last class, recall that our formula for potential energy from last class, potential energy was mgy. Okay, mgy. I'm going to orient the board real quick. Pause. Sorry. So from last class, we looked at one quick example at the end where we need to calculate the potential energy of an object that was raised out of a well. We want to know how much energy you gained.
Mr. How can I go back?
Your seat, you drop it now. Say again?
Can I go back really quick?
Can you go to the bathroom real quick?
Yeah, really quick. Okay. I'll be really quick.
Yeah, go. All right, now, the formula here, first, m is mass, g is gravitational constant. Y, remember y just stands for the change in height. The change in height. So if you go down from a higher height to a lower height, you're losing potential energy. So remember, the scenario we looked at with an object on a building, we compared the three different energies. Here it would have the most energy. As it falls, it loses potential energy. And then at the ground level, it has no potential energy, or right before it hits the ground. Okay? In the lab today, what we're going to do is talk about the idea of conservation of energy, where what's happening really is that it's picking up velocity on the way down, so it's gaining kinetic energy and losing potential energy. So there's a constant balance between energies. Okay, that's what we're going to do in the introduction for today's lab.
I'm confused with the y. What do you mean by changing height?
So for example, here, if, say the object is raised from ground level to 10 meters, the y value is positive 10. But if the object started up here at 10 meters and it dropped to the ground, then the y value is negative 10. It's lost that much energy. It helps you keep in mind the idea of conservation. Okay? Garrett.
Whatever happened to that other lab?
Remember it was just one we did together in class?
Yeah, we never had to handle it.
No, it's counting for your second quarter as your first lab. Everybody got a 30 out of 30 on it. Okay. So for your it's a nice starting point for your second quarter. Just keep it up, obviously. Okay. All right. So let's take a look at this. We have an ant. Okay, an ant. Remember how I said how they come up with weird problems? This is one of the things I was thinking about the other day. I was standing at the subway stop outside on my phone, and there was like a bug crawling on the ground carrying a big piece of like a twig or something. You ever see bugs carry objects that are huge? Yeah. And it started to like go up like a bit of like an incline. And I was thinking about this, like, all right, well, if we have something where the mass can change and the height can change, what can we come up with a problem? So that's where this one was from.
How are you using your phone?
Say again?
Outdoors.
No, outside. I was waiting outside. Outside upstairs, yeah. I was up at the 456 waiting for the mail. I was on the phone, and I was looking at the ground as I was going.
Last weekend, my piece had that thing where you like go like last weekend. I was thinking
about that.
that.
Nice, very nice.
We're gonna
use that. We're gonna use that exact example when we get to the next chapter. We're gonna look at We're gonna look at centrifugal motion. And centrifugal motion is an object that's being slung around in circular motion. So like your example. And one of the things I do for one of our labs that hopefully will go well is I do an example with rubber bands. And that's the cord, so it can expand and stuff, so you can see how that works.
Yeah, Mr. Howells, this week I was herding cattle and I was doing laughs and I was like, oh, I thought of this idea.
Funny. All right, so
Stop it, Mr. Howells.
an ant's potential energy keeps changing since it is constantly walking up and down hills and carrying heavy pieces of food that vary its overall mass. So at instant A, it's carrying 3.5 times its original mass. Again, it's carrying 3.5 times its mass in addition to its mass. So imagine this is real. Imagine you weigh 100 pounds, and I know we all probably weigh more than 100, but say you weigh 100 pounds. That means that you're now carrying not just 100, but an additional 350 pounds on your shoulder, which is kind of crazy to think about, right? Try walking with 350 pounds on your shoulders. It's pretty tough to do that.
That's not a big deal.
For Jack Dembler, I could carry 800 pounds.
Do you even, wait, I have a question.
That's the Gibson, bro.
I have a question. Wouldn't it be 300? It's not 350 plus 100, right?
In addition, I wrote in parentheses, in addition to its normal mass. It's carrying 3.5 times its mass in addition to its normal. So now it's got its 100 pounds plus 350.
So it wouldn't be 3.5 M?
It'd be like 3.5 M plus the M itself, giving you 4.5 M. Okay? So at instant A, the object, or the ant, is carrying 3.5 times its mass plus its actual mass. Okay, so at instant A, its mass is really 4.5 times its original. That was the question that Jeff just asked. Now, again, it's carrying n is some value. I'm doing this because this was on your test. It said if the kinetic energy doubles and if the mass doubles and the velocity doubles, what happens to the kinetic energy? It was multiple choice on the first page, which a lot of people got wrong. But you did actually. You could just pick values. You can always pick values. Think about it. Pick a 5.
Wait, what was the question?
Guys, hold on. Stop talking. I'm not going to go over the answer because we're recording and the test still hasn't been done by people. So I was hypothetical. Now, listen. The idea is this. You can use variables or you can pick values. So on the test, a lot of you picked values, which was fine. Some of you use variables to solve correctly, which I was very impressed by. Okay? So we're going to go over this with variables now to see the difference. So, you've got the ant is carrying 3.5 times its weight on its back, plus its own weight, so altogether its weight is 4.5 times whatever its mass is. Hypothetically speaking, you can call M1, doesn't matter. Now, that's at instant A. And then it's also at half the height that it is at instant B. Okay? So at instant A, we have that. At instant B, we'll call its height Y. So at instant A, what's the height? What is it? Half of? Good, or half of the B value, which was Y. So, right now, be nice, stop. My voice does that all the time. You guys don't do that to me. No.
Yeah, that's what you
So, again, it's carrying 3.5 times its mass in addition to its normal mass, and it's at half the height of that at instant B. So at instant B, we call its height Y, and we simply say that it's half that at instant A. Now, at instant B, it says it's not carrying food. You see that?
Yeah.
So what's the mass at instant B?
M.
Just M. Very good, Molly. Again, we have the mass at instant A, where it's got the food of 3.5 times its mass on top of its original mass. It's at half the height, so we call that 1/2 Y. At instant B, it's at the normal height, which we don't know what it is, but quote-unquote normal, and it's not carrying food, so it's got its original mass. Now, the problem says, at which instant does the ant have more potential energy, and by what factor? Okay? At which instant does it have more potential energy, and by what factor? So let's go ahead and look at our formula. Our formula tells us we're always going to use P equals mgy. Okay? Now, for part B down here at the bottom, we're going to see that m and y are just variables. So the potential energy is simply mgy. But at point A, what is the mass now? It's no longer m. 4.5 m.
MG.
G is still
Just as us.
good. And what is h? Or what is the height, rather? 1/2 y.
Which, oh, now I remember this, where it's the lawnmower problem. And then me and Tyson actually did solve, not numerically, but...
Apparently.
Why are you laughing?
Because I don't even talk about the problem we're doing, remember?
But I know what we're talking about, at least.
Yeah, this is, so you remember the problem.
Yeah, I now remember it. But we still, once we found it though, we still couldn't tell, I mean, we kind of like assumed.
Well, I'm going to show you that now. That's what we're going to look at right now. Okay. All right, so, just by inspection, it goes up by 4.5 times what it is, and then it gets halved. Okay? If I got, listen to this for a second. If I doubled something and then halved it, have I changed it at all? No. Is that clear?
Yeah.
Because double and half are reciprocals. But if I take something and quadruple it or multiply by 4, and then I have that, I'm still at double, right? I'm still at double. So here, this is clearly going to be bigger than this is down here. Do we all agree with that?
Oh yeah, we did do that.
Okay.
Yeah.
Now, 4.5 times 1/2 is just 2.25. So this equation up top just yields 2.25 mgy. That's what this becomes right here. So if the question says, by what factor does it increase? It's 2.25. What does factor mean in math? Raise your hand, tell me, Jack, what does factor mean?
It's multiple.
Exactly, something's multiplying by. So what are we taking the original, or the mgy, and multiplying it by? It's just this 2.5 right here. That's the only difference we're seeing. So at instant A, there's more potential energy, and by what factor? 2.25 times the actual energy at instant B.
Wait, sorry, how do you find that 2.25 again?
We do, we know that it's 4.5 here, and then it's a half here, so we bring our numbers out in front, take our constants, move them out, and multiply them together. 4.5 times a half is 2.25.
Okay.
Okay? And then we'll see we have mgy, mgy carries down. What property is that from that allows me to move this to the front?
Associative.
Associative, or either one actually, because it's parentheses.
Or distributive.
Not distributive.
Oh, commutative.
Commutative. Commutative I can rearrange, remember? And here, I'm also, guys, I'm not going to talk over you, stop. I am either arranging or rearranging with the commutative law, or I can think of it as moving my parentheses in this problem. Okay, we can do it either way, but in the end of the problem, what we want to note is that our factor it goes up by is 2.25. So, let's say you didn't know how to do this variably. You pick a mass. You say that the ant has a mass of 1. So now, this is just 4.5 times 1. You pick a value of a height. Say the height here is 20. So the height here is just 10. And calculate. And what you'll notice, if you do that, and you take your answer from here, and divide it by your answer from down here, you're going to get 2.25. Again, if you picked numbers, and you got a potential energy at point A, whatever the number came out to be, and then you have a potential energy at point B, and you divide those two, you'll still get 2.25 as your factor. It's the same answer either way. Livia. It said that at instant A, it's carrying 3.5 times its mass, and it's at half the height at that of instant B. So we call instant B y, just some variable. Say it's the height y. So what is this? Half of that. So if you want to call instant B 10, and say the height at instant B is 10, then the height at instant A is just 5. Okay, so you can pick numbers, that's fine, or you can use your variables that you determine or that you select. Okay? Alright, let's go on to the next thing. Is that clear as to what we're doing with potential energy? Okay, the lab today will help us go through the ideas, but remember, it's mg times whatever the height is. So if you're at a height of 10, you multiply by 10. If you're at a 20, multiply by 20. If you drop down to the bottom, what's your height? So is there any potential energy at the bottom? No. Okay? Now, in today's lab, we're going to see that the potential energy varies, and what we're going to do is we're going to look at a simulation of a person skating on a half pipe. So imagine a skateboarder going back and forth on a half pipe. What's happening is energy is constantly changing. At the top, when it's at the top of the half pipe, it's all potential. And then it gets to the bottom and loses all that potential, but it picks up a lot of speed, right? So there it's all kinetic. And then it loops back up and then back down. It's like the example you've heard in the middle school, or maybe another time in science, of a roller coaster and how your potential and kinetic energy changes along a roller coaster.
You said G is gravitational constant. I mean, that's -9.81.
Mm-hmm. Now, in these problems, remember, we're using positive 9.81 because we use the negative only when we were talking about remember we were talking about projectiles. Remember with like X and Y, an object is launched at an angle?
Yeah.
That's when we use the negative.
Should we go on a roller coaster?
Yeah, this way please, come on.
When you go on a roller coaster and then the rod actually backs kind of close to the back the car or whatever, does that
It's kind of stuck, you said?
Yeah.
You get
So like you're on a roller
the
coaster?
G-force, right?
Yeah.
Like stuck is in like, you feel like there's sweat holding you there? Or
No,
what do you
it's
mean?
like when you cradle a
I don't do
crossball.
roller coasters.
Okay, so when you cradle a crossball,
Uh-huh.
the ball stays in like.
Yeah, bro.
Centrifugal motion. Stop. Centrifugal motion. Remember when you talked about the lanyard?
Potentially.
When you cradle, are you going like this, back and forth?
Yeah.
You're rotating. When you rotate, you provide centrifugal motion and it keeps it out.
Hey, Mr. Allen, you laugh?
No, I play baseball.
Yo, baby, top cheddar. Yo, that shot was dirty.
I
say that though.
All right. Now, before we get into this, before we get into this next problem, let's talk about springs.
Lawnmowing is very necessary and beneficial.
about a spring and think about your pen or any object like a car that has springs on the suspension system. A spring, its real purpose is stabilization. That's what its purpose is. Now, it can also be used as like a catapult, and you think back to like medieval times, they would rotate the object till the spring or till the object had enough tension in it, then it would let go and it would launch the object or launch whatever it was. Whether it's like, a cannonball, or it was like an object that was lit on fire to cause the castle to burn, whatever it was. Those are examples of very basic springs. Now, in your car, when you hit a speed bump, the purpose of a spring and a damper system is to stabilize the car so that you're not doing this, right? When you see this in cars, believe it or not, like people think it looks like really like, I don't know. You see like movies where cars roll up and the hydraulics are really off? And you see that? Yeah. That means that there's probably a spring that's very weak, so it can do this the whole time, but there's no damper on it also, okay? Now, what we're going to look at in this chapter is the idea of energy in the spring and what happens when you compress or expand on a spring. Okay? So think about if you were to like literally stand on a trampoline, you stretch the trampoline down, right? You stretch it down, and if you jumped up all of a sudden, what would happen to the surface of the trampoline? Excuse me. Please, hurry around the room. If you stand on a trampoline, you start to like dip into it. If you were to jump, the trampoline would do what?
Come back up.
It would shoot back up, right? Because you were expanding the trampoline surface or expanding a spring. And when you let go, it wants to come back to its normal size or its free length. Okay? So let's write some information down. First, the length of a spring. Okay, the length of a spring, we call it its free length. Its free length. So if I said the free length of a spring is 2 centimeters, that means when you're not applying a force to it, when it's just sitting on the desk, it's 2 centimeters. Is that clear?
No.
Yeah.
No.
So this, imagine this is a spring right here, and this is the length of it, okay? The free length of the spring might be 5 or 4 centimeters. Now, if I take it, I compress the spring all the way down until it's a height like this. Now the height of the spring might be only 1 centimeter. So the actual length of the spring, when it's by itself with no outside force, is called the free length. All right?
So no pressure on the spring.
Exactly. No force. Let's say force for now. We'll talk about pressure in another chapter. So no force being applied. Now, if we do apply a force, what happens to the spring?
It compresses.
Yeah, it compresses. Now, we're going to look at a formula in a minute, and the formula that we're going to look at, dictates or tells us about the change in its length. So if the length of this spring is 5 centimeters and I compress it till it's 1 centimeter, what is the delta? What is the change? What is it? 4. Again, it starts at 5. I compress it till it's down to 1. Now it's changed by 4 centimeters. So the formula we're going to look at in a minute involves that change. Okay? Now, here's the formula we're going to use. Potential energy, and I'm going to put a little S here. What do you think S stands for? Spring. Okay? If you don't see the S, we're talking about mgy from the last part, okay? But again, this is a type of potential energy. Now, the formula for this is 1/2 kx squared. Okay, 1/2, and I'll explain what they are, kx squared. Now, x is the distance either compressed or expanded, whatever the delta value is. In your book, I think, uses this. I think your book writes it like this. Okay? I'm pretty sure that's how your book actually writes it, with a delta. But remember that this year we've been talking about x as our change in displacement. So we could just simply write an x down in this part and see for this year, if we had, say, a free length of like 20 centimeters and it drops to 12, our x value is going to be 8. Let's focus on the board. Our x value is 8. Now, the question is, what is the k value? Okay, what is the k value? What do you got?
It's the measured it's a constant of the spring.
What does that mean?
It's like the force that you
Okay.
so it's like
Thank you very much.
it depends on the spring. It's like you use it, you just springs of different materials with a different k value. Like so like it determines
What's the word you're looking for? Rigidity? K value is the following. It's the idea that, imagine a spring that was really wide. So a spring like this versus a spring like this. Don't they have different stiffnesses or rigidity, it's called?
Yeah.
Your book is going to call it, relax. Your book's going to call it spring stiffness, okay? So it's going to call it the K value or the stiffness of the spring. Now, a spring that takes a lot for me to push it down has a very high K value. It's like, remember with the mu value for friction? If mu is very high, it means that it's tough to push because friction is resisting. So when the K value is a very high value, it's tough for you to compress or expand the spring. Now, as Saj said, it depends on the spring. It depends on the length of the spring. It depends on the cross-sectional area. It depends on the thickness of the coils. It depends on the number of coils and the material also. So there's all these different things. Now, the spring itself is going to have a stiffness value that will be given to you. It's not going to be something you're going to have to calculate. You might be given PE and X and have to solve for K, but you're not going to have to say, well, there's more loops in the coils, or the coils are thicker, or the material is not metal, but it's, say, copper instead of aluminum. You're not going to have to worry about the material properties. So you're going to either be given the K value, or you're going to have to calculate K based on just the PE and the X values. All right? So again, for K, here's what I want you to write down. K is the spring constant. K is the spring constant. Okay, the spring constant. And its units are newtons over meter. And we're going to go over where that comes from in a later chapter. So for now, trust me on this one, but we're going to go over the etymology or the derivation of the units there in a later chapter. Now, yes, guys. Sasha.
That was the first thing I said.
Constant, yeah. But I wanted like this, people want to know what is constant, right? Gravitational constant. What is it physically? So when we think of this again, remember, and I want you guys to have physics common sense, not just numbers and know the formulas. A high K value means it's tough to compress that spring or expand that spring. A low K value means that I've got a very weak spring. So remember last class when Fernando took out the spring in his pen and I was talking about energy? That would be a very low K value. Because you could take the spring in your pen and break it easily, right? You could take it and stretch it so it's deformed. It's got a very low K value. But in your car, the springs that hold up your suspension system have a very high K value. They have to be able to support a very large amount of force or weight from your car. Okay? Is a very rigid or strong spring. And rigid or strong. Okay, so as K goes up, the strength of the spring goes up.
So the rigidity goes up as well?
Correct. Any questions on this so far? All right, let's go to our example now. By the way, it's potential energy, so the units that you come out with here are going to be joules still. Here's another question for you. Does it matter if X is negative or positive in this problem?
Yes, because I know there's negatives in the problem.
No, because it's
squared.
squared. It's squared.
It's squared. Careful there, Jeff. X is squared. So all that matters is the delta. So if you have a spring that is expanded 5 inches, it's a positive 5. If it's compressed 5 inches, it's a negative 5. But it doesn't actually matter for energy. It's going to matter later. So we're going to make sure that we're consistent here. Okay? Let's go look at this problem now. So, a spring is compressed. A distance. Oh,
What? They said your spring is
a spring is compressed a distance from its free length of 2 meters to a length of 0.5 meters. Again, it's compressed from its free length of 2 meters to a length of 0.5 meters. If the rigidity of the spring is represented by a stiffness of 50 newtons per meter, then how much potential energy is stored in the spring?
So the X is 0.5.
Okay? X is not 0.5. Again, let's figure out what we have here. Let's write down, we have the free length of the spring is going to be 2 meters right here. The actual length is going to be 0.5 meters. So you might want to think of this as like final minus initial. Okay, final minus initial. So I could say simply my final is 0.5 meters My initial is 2 meters.
Oh, it's
So what's my delta going to be?
But then it's 1 point. No.
What's my delta going to be here?
1 point, negative 1.
Negative, negative.
I knew to subtract this, so I literally thought it was 1.5. I don't know that.
It's all right. Now, that's going to be my x overall. Again, that's my x value for this problem. Again, remember, start with whatever the spring has been changed to, the final value, okay? And then subtract the free length from that. Is that clear? Again, we start with whatever it's been compressed or stretched to, whatever distance that is, whatever length that is, and subtract the free length. I'm not using FXF because free and final get people confused. Remember, this is really like final minus initial, right? That's why we do delta. The reason I'm not putting that there is because people see XF and they think that's free and then they mix these up, okay? So just remember current minus free, okay? Or final minus initial, as we've been doing all year. The current length of 0.5 minus the free length of 2. All right, that's my x value. The k value is given as 50 newtons per meter. Okay, 50 newtons per meter. What do I do? It's a pretty easy problem, right? Formula, PES equals 1/2 kx squared. Okay, what am I just going to do? Yeah, just plug on in, please.
Yeah, if I could get a drink, well, actually, what is this period now?
Yes.
So plugging all these values in here, we're going to see that we're going to end up getting a value here. What do we got? Somebody calculate for me, Jeff. What do we got? Mosh. 56 point, and it's positive, right? Because it's a negative squared, so we're going to have a positive in the end.
Yeah.
Remember, we're squaring the negative here. So this becomes positive, yielding a positive answer. 2-1? 2-1-5? No, 2-5, sorry. 2-5 or 2-1? 2-5, I wrote it wrong, sorry. Okay, 56.25 joules. Now, let's take a look at our units and see if this makes sense. First, we notice here, we're going to have a value, here for K of Newton over meter, and this is going to be a meter squared. So this is going to become Newton over meter for K times meter squared. So there's a meter squared up top, there's a meter down below. This meter cancels with one of these meters, leaving me with Newton times meter. Well, think back. Remember work? Work was F cosine theta absolute value of x. Well, this was Newton for F, meter for x. Here we have, again, Newton times a meter. And remember the unit for work was joules, so we have, again, a unit of joules here. Okay, another unit of joules. We're going to do a lot of these problems in the next section where we do conservation, where we're going to put together potential energy, kinetic energy, and then potential energy in a spring. We're going to do problems that involve all of them, okay? Let's do one more follow-up, though, since we have a few minutes real quick.
Wait, you mean next period or next? You said next section.
So we're going to learn section 5.3 after break. The lab today, though, is going to be a bit of an introduction for 5.3, okay? I'm trying that today, see how it works.
We have plus. We don't have plus tomorrow.
Say again?
We don't. Yeah, we don't.
No, you guys do not. All right, I got an idea, actually.
Hey, can you tell us our grade?
Oh yeah, can you tell me?
Not right now, guys. No.
Out loud, so we can.
It's a joules is very expensive. Oh wait.
Which is a little bit annoying, guys, because later in the year, we're going to talk about torque, which is Newton times meter, but it doesn't represent a joule.
Do you want to go like family?
Who's missing? Which one's the bathroom?
Paul.
Paul? All right. Take a reader for the intro, please.
I got it.
century is a law of physics. It states that the total amount of energy in an isolated system remains constant over time. The total energy is said to be conserved over time. For an isolated system, this law means that energy can change its location within the system, and that it can change form within the system. For instance, chemical energy can become kinetic energy, but that energy can be neither created nor destroyed.
All right, so the objectives for today's lab we're going to look at. We're going to first demonstrate the validity of this using a program on the computer. Second, we're going to determine the types of energy that a particle can have at different points. And third, we're going to determine the dependency or lack thereof of the velocity of the mass, on the mass of an object. Now, what I want to do today really is go through this lab in class, but I want to quickly go over the introduction so we don't spend time there. So first, energy of position. What do we call that when the position changes? Potential. Very good. So that's potential energy. Okay, potential energy. Energy of movement is called kinetic energy. Okay, kinetic energy. Now, here's where we haven't discussed yet. Think about this logically, please. Watch what I'm doing. If I were to take my hand and simply run across this table, it's going to build up heat, right?
Yeah.
So, I have kinetic energy because I'm moving. And something is slowing me down. It's friction. And it's giving off heat. So what happens is this. We don't ever lose energy. So if I take this remote and I slide it across the table, it didn't lose kinetic energy. It's not going away. It's just transferring. Again, you don't say, well, I had kinetic energy because it was moving and then it went away. So clearly it must just go away. No. The idea is this. The kinetic energy in the beginning is being transformed into some other type of energy. And that energy is usually heat when we have friction. There's usually heat that's given off. Okay? Or some sort of resistive energy. So look at it. Yes, very good. So friction in moving parts causes heat and wastes energy. Okay, friction in moving parts causes heat and wastes energy. Now, what kind of energy does the skater have when it's at the highest point in his path when it comes to the top of the half pipe?
Potential.
All potential, because it's not moving. Remember, think about a half pipe. Don't you pause at the top?
Yeah.
It's all potential. And at the bottom?
The fastest.
At the lowest point?
Zero.
What kind of energy? It's all what?
Kinetic.
Kinetic. Where's that noise?
That's outside.
Is that outside, really? Oh my
Yeah.
gosh. It's crazy, man.
I'm getting old.
All right. So, at the bottom, it moves all the time. Let's go down to the computer lab and finish up there.